this experiment we're going to carry out the complexometric determination of nickel using EDTA. We're going to be working with the hydrated nickel salt sulfate, which has the chemical formula NiSO4 6H2O. And the aim of the experiment will be to determine the percentage by mass of nickel in the salt. And we'll do this by carrying out a titration with EDTA. So the analysis relies on the ability of transition metals to form complexes with ligands. In this particular case, the ligand we're going to use is EDTA. Now, this is the structure of EDTA. You'll be pleased to know you don't need to learn the structure, but you should be aware that under alkaline conditions, it's a hexadentate ligand and forms a one-to-one complex with transition metal ions. So, under alkaline conditions, we lose the 4 hydrogens which are attached to the carboxyl groups, leaving 1, 2, 3, 4, 5, 6 lone pairs which can bond with a transition metal. So the nickel EDTA complex is octahedral in shape, and importantly the mole ratio is 1 molecule of EDTA to 1 nickel ion. So here's the balanced stoichiometric equation for the titration we'll be doing. It's simply 1 mole of nickel ions reacts to 1 mole of EDTA to form our nickel EDTA complex. We do need an indicator in order to identify the end point of the reaction. The indicator we're going to use is called murexide, and initially that will give us a yellow colour, but the end of the reaction will be identified by the change from yellow to a reddish mauve colour. So once we've got the volume of EDTA we need, the EDTA is a standard solution, so we accurately know its concentration. So we know the number of moles of the EDTA, the number of moles of nickel ion will be the same, and then once taking into account the dilutions, we can then work out the percentage by mass of nickel in our complex, and then compare that with the value we'd expect it to be. So the first thing we have to do is to add accurately about 2.6 grams of the nickel salt. So you put the beaker on the balance, zero it, then add the nickel salt till you get near 2.6 grams. Okay, so that's 2.56 grams, so that's close enough, I'll record that. So the next thing we have to do is to dissolve the nickel salt in approximately 25 cubic centimetres of distilled water. Now, we're just going to use the markings on the sides of the beaker to judge the 25 cubic centimetres. Then once it's fully dissolved, we'll transfer it to a 100 cubic centimetre standard flask. Okay, so that's all the nickel salt completely dissolved. So I'll just wash down the glass rod so we don't lose any of the solution, and transfer the dissolved salt into the 100 ml standard flask using a funnel so I don't lose any. Wash the sides of the beaker and the funnel a couple of times. And fill it up to the start of the neck with the water, and then as I get close to the 100 ml mark, I'm going to use a dropping pipette for added accuracy to make sure I don't go over. Okay, I'll stop on the flask, invert a couple of times to make sure that it's a homogeneous solution, and that's our standard solution prepared. Okay, we now transfer 20 ml of the nickel salt into the conical flask. We have, of course, already washed out pipette with a few mils of our nickel solution prior to getting the 20 mils for transferring. We then add very roughly 0.05 grams of our murexide, which is going to be our indicator for the titration. So that's a very small amount, certainly no more than that. Okay, so don't actually have to weigh out 0.05 grams, just no more than that. So we add that, and then we add 10 mils of ammonium chloride, and that can be measured out using a measuring cylinder. Give it a good mix, and you see our starting colour is a nice yellow colour, which is the colour produced by the murexide bonded to the nickel. And then, having added the 20 cubic centimetres of the nickel salt, 10 of the ammonium chloride solution, we make up the solution to roughly 100 cubic centimetres using deionised water, just using the markings at the side of the conical flask. Now, this doesn't affect the number of moles of nickel in the conical flask, so it doesn't need to be too accurate, just round about 100 cubic centimetres. And now we're ready to start our titration. And stop. Okay, so I've already recorded our starting volume, which is 2.2 cubic centimetres, and the instructions tell you to add approximately 15 cubic centimetres of the EDTA. So I'll take it down to about 17. Started at 2, so going down to 17 is approximately 15. Okay. We then add 10 cubic centimetres of ammonia, just using the same measuring cylinder as you did for the ammonium chloride. This is to make sure the solution is basic, as the EDTA works best in a basic solution. Okay. Since this is a rough titration, I'll just add about 10 pieces at a time to find out the rough volume required. And as you see, the solution has changed colour now from yellow to this reddish brown colour, and because of the rough titration I have probably overshot it slightly. So my final volume there is 20.6. So I've added 18.4 cubic centimetres. Okay. So I'll now proceed to do several accurate titrations until I get 2 which are within 0.1 of each other. So let's assume I've just done my titration and I got results of 17.6 and 17.5. So they're concordant, so taking the average of those two gives me a volume of 17.55 cubic centimetres for the EDTA. Now, to determine the percentage by mass of nickel in the sample, so the number of moles of EDTA is the concentration of EDTA times the volume. The concentration was 0.1. The volume was 0.01755, which gave me the number of moles of EDTA as 0.001755 moles. Now the number of moles of nickel ions, if you remember, the nickel and EDTA react in a 1-to-1 ratio. So we've got the exact same number of moles of nickel, and that was in the volume of nickel we put into the conical flask for the titration, which was 20 cubic centimetres. Our entire nickel sample had been diluted to 100 cubic centimetres, so the number of moles of nickel is 5 times that, which is 0.008775 in the 100 cubic centimetres, which was the entire sample. That entire sample was 2.56 grams. That's the number of moles of nickel. So the mass of nickel would be the number of moles times the GFM. So 0.008775 times the gram formula mass of nickel, which is 58.7, equals 0.515 grams of nickel. So the percentage nickel, so out of that 2.56 grams, 0.515 was nickel. So 0.515 divided by 2.56 times 100 gives us a percentage of 20.1%. When determining the theoretical percentage by mass of nickel in the nickel sulfate, you're going to use the equation percentage nickel equals mass of nickel in the formula, which will be just 58.7 over the gram formula mass times 100. Now it's important when you're working out the gram formula mass that you take into account the 6 moles of water molecules that are contained within the hydrated nickel salt. So your gram formula mass will be the nickel plus sulfur plus 4 oxygens plus 6 H2Os. And I'll leave you to work that out yourself. Compare it with the value you got from your experimental results and then complete the discussion.